set.
Right. Okay. All right, thanks. Hi, everybody. I'm Ben.Cotton. I'm a programmer here at Credit Suisse, and I work specifically on the capital markets technology team. I'm also Credit Suisse's representative on JSR 107, which is the new Java caching API standard. If you notice on the slide, I have the word new in quotes. That's because JSR 107 is new only in its most recent sense. The specification was originally the original specification request went out in 2001, but for whatever reason, the spec became inactive, and is usually the case with the urgency to push forward new standards. That urgency usually comes from an existing delinquency of other standards, and that's especially true here with JSR 107. It's a new urgency to get pushed as a standard is because Java is frankly a weak participant in capital markets caching solutions. Most of my clients, the big sell-side banks, when they want to consume price ticks from the ECNs, they're going to use something like KX Systems KDB, and they're going to use Q operators, Q programming language operators, to process those low latency events, because Java frankly hasn't stepped to the plate with a sound and complete solution for caching in capital markets use cases. What I want to do is share with you some of the history of those delinquencies, some stories about the physics and the mathematics of low latency as it applies to the capital markets use case. We have one dramatic story I think you'll find pretty entertaining. I really like this Java users group. I've only been to a couple of meetings, but they've been really, really spectacularly entertaining. I went to the Scala presentation, very well done and entertaining. I went to the gentleman who gave the functional thinking presentation, spectacular. And of course, I went to your presentation. And when you were using JMS on the public internet to steer that race car from your iPhone, I thought, oh wow. So anyway, I'm actually a substitute speaker for an event that got canceled. But let's get started with what I'm going to present with you. So I'm going to sit down because I'm too big to stand the whole thing. All right. Early major problems, okay. In the winter of 1997, okay, Java had a servlet API firmly in place. It had a JDBC API firmly in place, and it had an RMI API fully in place. And with those three little pieces of technology capability, the Java machine from Sun went out and told the world, web applications are ready. Now, here's a case where they're to be proven wrong, very dramatically. The week before Christmas in 1997, the web-facing order management system at Amazon.com repeatedly crashed. All right, availability was severely impacted. Millions of dollars in potential revenue were lost. Credibilities with their customers were damaged. And just to put it simply, Amazon.com cannot go down the week before Christmas. That's all there is to it. So that's a big pie in your face for everyone who said web applications are ready, because, well, they weren't ready. Okay, an urgent, immediate solution was required to correct legacy application architectures so they could reliably and performantly operate at internet scale. These architectures that scaled in the data center aren't going to work when you have millions of simultaneous HTTP sessions coming through the week before Christmas. And not only they're not just surfing HTTP sessions, they're transactional HTTP sessions. So they're depending on back-end systems to transact business, okay? That didn't work in the winter of 1997. So we needed a silver bullet, and we needed it fast, and enter caching technology. So what is at stake for caching solution providers and their customers? All right, caching technology providers had a huge incentive to deliver 100% sound and 100% complete solution. What was at stake was the World Wide Web as a reliable and performant application platform. 5 important things were immediately needed. We needed to deliver to application architects and developers the capability to rapidly implement the caching provider's solution. Okay, wasn't enough that they could build something. They had to empower existing architects and existing developers to use their solution to quickly build and deploy. They had to offload the database. This was an ultra-urgent requirement. The reason Amazon was crashing was because to commit a transaction, you have to physically touch a disk from a database server, okay? You can't do that with millions of transactional simultaneous HTTP sessions. Your system will fail, okay? They had to deliver solutions so you could scale up. How can I make a cache's in-process heap as big as possible? and they had to scale out. How can I distribute my cache so it can be distributed across multiple processes? And most importantly, they had to generate a confidence that they could buffer against load variability. Amazon.com worked perfectly in 1997 for 51 weeks. Okay, but that week before Christmas, the show stopped. All right, now given that, I want to talk with you a little bit about a brief history of the data locality and latency problem, because this is very relevant to capital markets use cases and their needs for caching vendors. Okay, caching vendors have to supply us solutions that allow us to move our processing as close as possible to the data as possible, and we have to be able to access that data with the lowest possible latency. Physical constraints come into play with our requirements for these use cases. All right, the data locality problem. In a single sentence, it asks this question: how much am I willing to pay to have my data as close as possible to processing resources? All right, the absolute closest you can have your data to processing resources is in the registers and the arithmetic logic unit of the central processing unit. Now, moving the data further away, you can be very close on circuit, on chip, to the registers and the logic units by creating an L1 cache, okay? Moving a little bit further, still on chip, you can have an L2 cache. And you can come off chip, okay, and have main memory or RAM. But you pay a price as you move away, okay? When you go onto RAM, you have to cross a physical circuit board, a data bus, to get to the central processing logic circuitry, okay? So, but the motivation for moving the data away is you can accommodate more data, obviously. You can only support maybe just a few K in the registers, support a few gig in the RAM. All right, moving further away, let's say I have two processes, okay, sitting on a local system, okay. Now, I don't want to have the data so close that I keep redundant copies in each process's user space. Unix has a IPC facility where you can use shared memory between the processes. So that's moving the data further away, even further. Okay, still very close. The price you pay there is you have to go through a kernel API with a system call. Like you have to do a shared memory create, shared memory attach, shared memory op. Okay, and that's a very clumsy API to work with if you want to work compellingly with data. But again, it's a method of moving the data, keeping it still close to the processing, but not that close. Further still, you have a single, you have three processes now on one platform. Okay, so now I can introduce TCP/IP semantics. All right, this is only one IP address. So if I have a data server listening on port 1521, I can specialize that process for its data needs, and I can keep these other processes small. So that's moving the data further away still. Finally, I can have three IP addresses within a local network. Okay, I have to go through physical network semantics over the same TCP/IP API. But again, this is moving the data further away from the processing at the cost of just a few network hops that are local. Now, finally, I can get a huge data space and use public data sources. Okay, so now I'm using TCP/IP over a wide area network. Now, typically, I won't be allowed to use TCP/IP directly. I have to use an application protocol like HTTP because most network administrators aren't going to let you use TCP/IP directly on the public internet. So the idea is this: we can accommodate more and more and more data by moving the data further away from the processing, but we're going to pay cost elsewhere that we're not tolerant of in capital markets use cases. Okay, so let's talk about the latency problem. We looked a little bit at the data locality problem, how we can get more data to process if we move it further away from the processing resources. Given that data is available, how fast can I access it for processing? That's the big question we ask for low latency applications. So let's look at the registers. We can only accommodate like 1 KB of data size. This is an old chart, but just so forgive it, just scale it up a little bit. The symmetry is the same. But with that data in that, we can access it in 1 to 3 nanoseconds, which is virtually zero time. I'm paying an almost zero cost to access that data. On chip, again, almost zero cost. Even on off chip, it's almost a zero cost. Now, when I go to main memory and I have to cross a physical data bus, I have an order of magnitude jump, but we're still talking about 10 to 60 nanoseconds, which is almost a zero cost. Finally, look what happens when we have to go to access on a hard disk. All right. several orders of magnitudes difference, 3 million nanoseconds, intolerably slow for low latency cases. Now you say 3 million nanoseconds. Now that's only 3 milliseconds, okay? For some views, 3 milliseconds is acceptable latency, but for us, we don't tolerate it, okay? I want to give you a little bit of math. Now this looks kind of intimidating at first glance, but it's really quite simple. It gives you a basis for architecting latency solutions given your resources. This is a equation that was first introduced by Vilfredo Pareto, who was an Italian mathematician in the 19th century. And what he was doing was he was trying to get expected return on his Italian real estate speculation, okay? What he did was he outlined a space where there's n possible events in the space, and each of those n events have a probability of occurring. If you add up the probability of each of the I events in n, that probability adds up to 1. So a complete outcome is determined, okay? So what we want to do is say, given this model, we want to generate our notion of what expected latency is, okay? If you take any probability in statistics courses, this looks like what's known as a weighted expectation expression, okay? So let's say our desk says to us and says, Ben, given the resources you have, we want you to generate a latency solution that gives us an expected latency of 0.4 milliseconds. And I say, okay, well, what are my resources to do that? So they say, Ben, we're going to give you a level 1 tier where you get virtually zero cost. It's going to be on-chip, on-heap latency. We're going to basically call that zero. It's going to be less than 5 microseconds, which we're basically going to call 0 milliseconds. And the other participant in your caching levels is L2, which is going to cost you 2 to 3 milliseconds, which basically acts like disk. Okay. So given this, I want to engineer how much of my resources do I want to put in L1 so that I can meet the 0.4 millisecond mandate from the desk. If I allocate 80% and use this expression, well, 80% times 0 costs, 20% of the time I'm going to have to pay the 3 millisecond cost. So my expected latency is 0.6 milliseconds. Still too slow to meet the 0.4 millisecond mandate from the desk. So I say, well, what happens if I partition 90% of my resources to L1? Then my latency is 90% times 0 is 0. 10% of the times I have to pay the 3 millisecond cost. So that total value is 0.3 milliseconds, which is better than what the desk asked for. And basically, you can stop your allocation right there. I could just go to the desk and say, I can get you 0.3 milliseconds if you give me 90% of my resources in L1. That's going to be very expensive to them, but once they hear they can get 0.3, they'll always buy it every single time because it's the milliseconds that are precious. All right, moving down, I want to talk a little bit about the physics of low latency, okay? I'm not really qualified to talk about physics, but let me mention about Wall Street is dominated in this space by physicists. There are 2,000 PhD physicists currently working on Wall Street. It's impossible for the U.S. colleges and universities to meet the Wall Street demand. It turns out that many of these PhD physicists are from former Soviet bloc countries. Now, if you ask these algo quants, and they're at every house, every one of them has all these, they're all bald, they're all male, they all have beards, and they're all from the former Soviet Union. And it's exactly what it's, I'd hate to be non-politically correct, but that's exactly who they are. And if you ask them what they worked on while they were in the Soviet Union, they'll very very calmly and very directly say, we worked on trying to defeat stealth. And I was fascinated by that. I said, oh, did you have any luck with that? No, we couldn't do it. Okay, so it's interesting now that the pride of like Karl Marx and Vladimir Lenin, these people who were trying to defeat stealth and used to design hydrogen bombs to blow us up, they're now here in our neighborhood designing low latency, high frequency capital markets trading algorithms, and they're doing it very successfully. So Wall Street will go to the former Soviet bloc. All's forgiven. All's forgiven. If you bring the talent, we'll bring you the use case. Write us the algorithms. So that's where we stand. It's a very interesting and dramatic. Karl Marx and Vladimir Lenin must be rolling over in their graves. But anyway, let me tell you about some of the algorithms that are famous that they created. They've got really weird names, and I don't know why they're named. But one of them is Cherokee Nation, Marco Polo, Boston Shuffler, Frog Pond, Carnival, Twilight. If you ever heard these if you ever hear of these code words in high-frequency trading circles, these came from Soviet-born physicists, okay? And they're now transacting international global capital. Das Kapital lives in their skills. Now, I want to show you something that's the bottom line. Great latency equals great location. Now, here's a really bizarre and dramatic story. Okay, there's this place called the New York City Carrier Hotel. Now, it's a place where algorithms check in, but they don't check out. And I've given you two little references here. Maybe Frank can distribute this stack at the end so people can view them later. But this is a really dramatic story. The Carrier Hotel is where AT&T, back in the 70s, laid all their dark fiber, okay? And it's the New York City, it's the entry point of the internet into New York City. Now, AT&T divested and they created this Death Star symbol. This used to be called their Darth Fiber. Okay, that's all this Death Star motif, and they had all these little crazy games on the Star Wars angle. But AT&T never had a business plan to sell this dark fiber, so eventually they sold the address, which was this hotel, to New York City, and unfortunately, this hotel became a place where challenged communities were set up to be given shelter by the city, like homeless people, people who had drug and alcohol problems. They were set up there. But at any rate, let's see what happens in the 80s and 90s. Something very interesting happens. Okay. Now this is the geophysical map of 7 of the largest sell-side investment banks in New York. Okay. Now what's more important is the relationship of these banks to the Carrier Hotel. Because remember, the Carrier Hotel is where the internet enters New York City. Homeless people, alcoholics, crackheads, they're there now. Okay, but watch what happens. Okay, superimposed over the addresses of these elite and prestigious sell-side investment banks are their algorithms. This is where their algorithms live. Now, one of the physicists who sponsors the Cherokee Nation algorithm at Goldman, okay, he had a problem. He said, given that the international price ticks are coming through the plumbing of the Carrier Hotel, Barclays Carnival algorithm is getting an 80 microsecond lead on these price ticks. They're getting them 80 microseconds faster than us because they're that much closer to the Carrier Hotel. So the Soviet physicists at Goldman went to their management and said, is there any way we can beat Barclays' advantage because they have a physical advantage? Well, you won't believe what they did. They checked into the Carrier Hotel. So amongst alcoholics, crackheads, and homeless, the elite of the elite, Goldman Sachs tears down a floor, introduces all new air conditioning, reliable plumbing, turns on air conditioning for all the tenants everywhere, says we want our algorithm here because we don't want Barclays to have an 80 microsecond advantage. And that's an amazing story. If you go back to this link here, look up this story by Kevin Slavin. Okay, it's a great story. He tells the whole story in very elaborate detail. But anyway, going further, eventually Citi and Deutsche Bank found out that Goldman went to the Ma Bell plumbing place, and now all the algorithms now live at the Carrier Hotel. Only in New York, right? So, all right. But that's a great story, I thought. Okay, here's a bottom line. Okay, caching efficiency can be measured like this. If your hits are in your cache are a high percentage of your total hits, then you have an efficient cache. That's the bottom line. And when you have high efficiency, you can offload the database a great deal, and you can get great performance. Now the question is, how can we best make this happen with Java caching technology? All right, I don't know about a lot of you guys, but I found Java technology to be pretty delinquent in terms of capital markets use cases. I mean, we have Java caches that house reference data. We have Java caches that host treasury benchmarks. But high-frequency price ticks, okay, those are still delegated to proprietary systems with million-dollar licenses we have to pay, and because Java's delinquent in being able to meet those demands. All right, let's move forward. When you have a distributed cache, we're talking about L1 and L2 and where your caching resources sit. When you have caches that are partitioned and distributed, you have to have what's called a coherency protocol to keep the caches consistent. All views on what the cache contains have to be consistent, okay? They have to be available, and they have to be tolerant to partition failure, okay? And that's very important because all three of these things have to be present in some form. Now, there's trade-offs you have to make. But one thing I want everyone to be aware of is don't ever let a caching vendor tell you that they can sell you something that's simultaneously consistent, because it's physically impossible. And it should be a red flag if they try to do that, because they can't do it physically. There's this theorem in computer science called Brewer's theorem, and it's been abbreviated to be CAP theorem. Professor Brewer from Cal Berkeley said that he had a conjecture that for a distributed computer system, it is impossible to simultaneously provide consistency, availability, and partition tolerance. Now, let me just give a quick example of what's meant by that. Okay, let's say I want to start a simple caching service. Okay, Ben's going to start a cache. It's a birthday reminder service. Okay, you call me, okay, at t=1, and I'll write down on my ledger the name of the birthday you want me to remember, the name and the date of birth. You call me back at t=2, and I'll give back to you that information that you gave me earlier, okay? This system lacks availability, because what if two people call me at the same time? Now, to solve the availability problem, I hire my ex-wife, okay? So now if you call the service, I'll put the name in if I get the call, and she'll put the name in if she gets the call, and either way we'll give you the name back. But this lacks consistency, because what if at T1 you call me and I put the name in my book, and you call her back at T2, but she doesn't have the name in her book yet because it's not consistent, okay? The views of the data are not consistent. So me and my ex-wife add a coherency protocol to this system, okay? We say this: we're not going to have individual books, we're going to share the book, okay? So this way we have consistency and availability. We think we're going to have a good service now. Of course, me and my ex-wife inevitably will get in a fight. She'll stop talking to me, okay? So our elegant coherency solution is useless. We have a partition failure, okay? She's not going to talk, and there's nothing you can do to fix that. So how do caching vendors overcome Brewer's theorem? You can't simultaneously provide all three. They do it with what's called eventual consistency. So you want to hear their specifics of how do they implement eventual consistency. They want to know, can you promote to strong consistency? How do you do this with local transactions, explicit locking, XA transactions, etc.? And if you go further down the compromises, you can say, do you have any notion of partition healing, sort of like counseling? Like the partitions can reconnect and rejoin and be healthy. So they cannot possibly sell you this as a simultaneous solution. Computer science says it's impossible, and computer science is correct. Okay, let's look briefly at some of the existing APIs that accommodate Java caching. Okay, Hibernate as a technology. To be honest, I'm not too super familiar with JPA and DAO. Okay, I know this. Hibernate is often you use a caching vendor solution to act as an L2 cache for Hibernate. You know, you have your object model. You have an L2 cache, and you have Hibernate's back end, which is typically a relational data store of some kind, a system of record. Hibernate plugs in well, but it didn't used to play very well with clustered partition caches. Hibernate 3 now includes something called the Cache Region Factory in their service provider interface. This goes a long way to making Hibernate very strong in terms of supporting distributed caches and clustered caches. Okay. All right. Well, Enough now of the theory of caching. I want to move on to talking about JSR 107, which is the new standard Java caching API. All right. Now, before JSR 107, all the caching vendors provided basically proprietary APIs. Okay. If you wrote caching code, your code suffered from vendor lock-in. Now, just like JDBC solved this problem for the RDBMS community, JSR 107 solves this problem for the JCache community. Okay, so imagine writing to Oracle's proprietary data API or Sybase's TDS, or imagine writing directly to CTLib rather than JDBC or whatever Oracle's proprietary mechanism is. You're writing to a vendor's lock-in. Okay, so JSR 107 gives to the caching community what JDBC gave to the RDBMS Java community. JSR 107 is completely open. It's typically the Java community process requires its expert group to communicate privately on a private jcp.org expert group forum. JSR 107 is completely different. We're hosted publicly on the Google Groups at that URL. It's a public expert group forum. Every flame we ever had with one another, every whim we ever thought of, every notion, every musing is publicly documented. Okay, looking at JSR 107, we introduced a new package hierarchy. We have javax.cache. That's now going to be available to you. The central interface is called cache. JSR 107 develops. We use java.util.serverloader, which is only available in Java 6. So Java 6 is required, Java 6 or above, okay? JSR 107 is going to be in Java EE7, which is due at the end of 2012. So if you have a favorite EE container, WebLogic, JBoss, if that container becomes EE7 compliant, it's going to have JSR 107 as an implementation in its offering. And if you're willing to take down like a reference implementation and use Java EE6 or Spring, you can start using JSR 107 immediately. Okay, and it's usable like any Java-based app. Okay. What's that? Okay, the specification leads, okay, are Oracle and Terracotta. Okay, but to be blunt, there's a whole universe. Well, one thing about JSR 107, it has 3 members of the expert group who are directly from Wall Street. I'm looking now, I see David Mazakowski from Citigroup. David sits on JSR 107. I represent Credit Suisse. And Billy Newport from Goldman Sachs all sit in there. We sit there and we pretty much throw tantrums in the community forum about your delinquencies. All right? And we're telling the big players. We're telling it to IBM. We're telling it to Oracle. We're telling it to Terracotta. We're telling it to Red Hat. We're saying, look, Java is not a significant player for our use case. If you accommodate our use cases with something that's sound and complete, we promise you we'll be your best customer. We're everybody's best customer once you satisfy us. Okay, so it's being pushed by a lot of angles. Everyone's tired of auditioning and caching providers and writing their own facades to delegate to the proprietary APIs. We're sick of it. It's a delinquency in the Java community. It's shameful. So we want to give some incentive to these caching providers to write a standard. So that's, maybe it's a little harsh, but that's just how it is. Really. So, all right, let's look at it. It's okay. Finally, after years and years, Terracotta and Oracle designated 2 full-time employees, Greg Luck and Yannis Cosmopoulos, to develop the spec. It's developed completely in the open. 15 expert group members. 20% of those expert group members are from Wall Street. Okay, lots of healthy debate, lots of little flames go back and forth. It's civil, but it's intense. The spec is completely open, free to use and implement any way you see fit. The reference implementation that we're building is Apache 2 licensed, and the test for compatibility kit is also Apache 2 licensed, just for information purposes. Let's see. Expected implementers. Now, these are the big Java caching players, okay? You have Terracotta with their ubiquitous EH cache product. You have Oracle with Coherence. You have JBoss and Finispan. IBM with Extreme Scale. A big contributor, SpringSource and Gemfire. You've got GridGain. You've got Tmax. You've got the Google App Engine and their Guava caching capability. Anyone use Guava here? It's very strong stuff. They're pledged to be JSR 107 compliant. And you also have SPI Memcache and their Memcache client. Okay. Getting started. If you want to get started, we have our artifact up in Maven Central. So if you want to pull down our API, just put this tag in your build environment, and you can pull it straight down. You'll get our API. Looking at everything that we're doing, everything's out in the open. And in terms of code artifacts, in terms of the specification, all this kind of stuff, we have it all up in GitHub at this URL. Okay. Let's see. It's kind of blurry, isn't it? Anyway, if you look, this is our Java docs page for the 0.6 snapshot of what we're doing. Okay. If you look in the far left corner there, we have the package that's presented there on the main page, javax.cache. We have a rich set of annotations. We're building a capability so that if you want to write, if you have existing code, that you want that code to be subject to caching consequences, you don't have to write JSR 107 Java code. You can decorate your existing code with annotations from the JSR 107 package, and those caching consequences, you have to be in an intercept, you have to be in a method level intercept, but those caching consequences will take place as a result of annotations. I can't even read that. What does that third one say? Cache event. We have a lot of cache event processing capabilities in our API. If you look down that left tree in the far west of the page, you'll see a bunch of interfaces that end with listener. Okay, we have a listener for just about every cache event. You create a cache entry, you can listen for it. You remove a cache entry, you can listen for it. You update, read, access, all this kind of stuff, all these listeners. But anyway, this is our Java doc page. We think it's going to be a pretty sound and complete and capable standard for doing caching operations with Java providers. Okay, let's see. All right. Looking at some of the features, one of the API is going to support atomic operations. It's going to support them both transactionally and in terms of entry processors for exclusive atomic compound operations. The methods are similar to what you'll find in java.util.concurrentMap. Okay, we have read-through caching. Okay, obviously. Okay, if you do an access and the data isn't present at this level, the API will transparently seek wherever to wherever it finds the hit. We have write-through caching. We have both synchronous write-through caching, which is where the flow of control is kind of like not doing anything else but writing through to the back-end system of record. And we have what's called asynchronous write-through, which acts sort of like a write-behind capability. You can go off and do other processing while the implementation writes through to the system of record. We have a rich set of cache event listeners, and we have a statistics capabilities. One of our packages is called javax.cache.mbeam. So if you're using standard JMX mbeams, we have a package that gives you, this is turned off by default for performance reasons, but if you want, you can deploy and write your own mbeams that can interact with statistics mechanisms that we've set up in this package to measure caching statistics. Here's a huge one for us, and it's one that David and I fought explicitly very loudly for. Transactions, including all isolation levels. Now, a lot of these Java caching use cases are a bunch of kids worrying about, like on a distributed internet game, where their monster position is being cached correctly so that their shot hits it with the right coordinates. And like, Netflix caching applications like 12 indexes into Schindler's List is to see who's watching Schindler's List simultaneously. That's fine and good, but those aren't high-stakes transactional ways to host data. We want to see if you are capable to host capital markets data. International capital. Can we access and mutate safely with having our data cached in your solution? We have caching annotations, which gives you a nice way to, have caching consequences in your code without writing literal JSR 107 Java code. And we have generics. Everything's type safe, as you would expect with generics. Okay. Here's a huge thing, huge for capital markets. A JSR 107 compliant caching implementation is transactional in two important but different senses. All right. One, your compound access mutate operations against a cache entry are guaranteed to be exclusive and atomic. Okay? Don't let them sell you that, oh, yes, it's exclusive and atomic. They have to pass our test of compatibility. Okay? If they don't pass the test, they're not JSR 107 compliant. Okay, so don't worry about their sales pitch now. If they're JSR 107 compliant, clause 1 is guaranteed. And here's another super important one. Compound operations against a cache are guaranteed to preserve transactional ACID properties. The full scope of traditional transactions are ACID properties. First way you can achieve it with the cache entry processor interface. Second way with the old, reliable javax.transaction.user transactions. To be JSR 107 compliant, the caching providers are going to have an implementation of that, okay? Let's see what this means further. Okay, more important to note, all isolation levels are guaranteed, okay? Even your most extreme pedantic isolation use case, and only capital markets use cases have these crazy pedantic ones that are like way out there in extreme. And the caching vendors don't want to hear it. They say, oh, our use case doesn't accommodate it. Well, our use case does. Do you want to be our caching provider? Or do you want us to keep paying $1 million license fees to KX Systems? Because we'll keep doing it if you're not sound and complete. We're not going to risk money on your caching solution. This is what this means, okay? TX read uncommitted. If you have no tolerance, or if you have complete intolerance, if you don't care, just specify I'm willing to read TX. I'm willing to read uncommitted data. You can specify that. Okay. TX read committed. If you are intolerant of dirty reads, like every financial use case is, okay, you can specify that you're dirty read intolerant by specifying that isolation level. Same for these other higher isolation levels that only exist for our use cases. I'm going to give you a quick example. Whoops, did I do this right? Hold on. Let's see. Yeah. Okay. Here's an example. Let's say I have this JSR 107 JCash entry. Okay. It's a savings account. I'm hosting $5 in the account. Okay. I have two transactional threads. Transactional thread 1 is on the far west, time going downwards from the top, and transactional thread 2 is on the far east, going downwards from the top. Now let's say at time equals 0, the value in the cache is $5, and both threads begin transactions. At time equals 1, thread 1 mutates the value in the cache. It credits it $1. So the cache becomes $6, okay? Now, the container is obligated to mark that cache entry as dirty, okay, because it was mutated without being committed. Now, going further, at time equals 2, thread 2 reads in the value, and it reads in 6. At time equals 3, both do more processing, but at time equals 4, transactional thread 1 that mutated the entry rolls back. So the entry goes back to 5, but it's too late. Transactional thread 2 had already read the value of 6. It commits with the value equals 6, and what happens? Your data is inconsistent. All right? This is a minimum capability that has to be able to be done by a caching provider. Otherwise, no financial use case will engage with it at all. You have to respect people who are intolerant of dirty reads. We're some of those people. Okay, how would you code it? I don't want to go into this too much great detail. It's very simple to code this. For transactional thread 2 to be guaranteed that it won't endure a dirty read, all it has to do is build its cache with a javax.cache.transaction.isolation level read committed. Means I'm only willing to read data that's already been committed by your caching container. Okay? From there, you use the very familiar user transaction API from javax.transaction, the JTA. You construct a new version of your JSR 107 provider's user transaction implementation with a reference to the cache that you just created with the read committed policy, and then you just process it. So when you do the cache.get on the account, you'll block until transactional thread 1 commits, okay, or rolls back. So here's how it looks. Here's how it looks when we execute that code. At t equals 2, we're not going to endure a dirty read. We're going to block because we're intolerant of dirty reads. And the container guarantees that we won't be given that access until the data that was muted either commits or rolls back. Now we see at t equals 5, the data did roll back, so transactional thread 2 will be allowed to access it, and it gets the safe value, the value that won't cause data to be inconsistent, the value that won't cause bankers' pagers to go off in the middle of the night and programmers to get fired. Okay. Now, how about other cases? Okay. Can we use JSR 107 to accommodate all transaction isolation tolerances and intolerances? What about those rare transactional use cases that have extreme TX isolation demands? For example, if I have an intolerance to phantom reads, which occur without relevance nowhere but in the capital markets use cases, okay? Answer is yes, all right? We are sound and complete with regard to accommodating all transaction isolation demands. What about multiple dynamic views of the same cache with different demands? Yes, we're sound and complete with regards to accommodating that concern. For example, let's say we have a retail desk and an institutional desk, okay, and shared in common is a cached high-yield credit portfolio of 3,000 bonds, okay? Retail desk does thousands of trades daily. Okay, each trade just a few milliseconds to transact. Average trade $5,000. All they need is read committed isolation. The policy of that desk is to churn and burn. Okay, if we get a phantom read, who cares? Just trade more. Okay, it's not going to cost us anything. On the other side, you have an institutional desk. Okay, these guys do the big bet the bank swaps. Okay, so if Credit Suisse is going to do a swap with Goldman, okay, and it's going to be a $10 million credit swap, okay, we are intolerant of any retail trade messing us up, okay? So we specify transaction isolation serializable, and we're guaranteed that we won't have to worry about mutations in the portfolio done by the retail desk for the 4 seconds that we need to conduct the metrics for a fair swap. We're guaranteed that we get it. Very, very important. Sound and complete with regard to all the transaction isolation use cases. All right, moving forward. How to please everyone. We have some features. Store by reference is a feature that we allow. Okay, you know, in the typical map, it's a store by value. Store by reference, you get much better speed. XA and local transactions are an optional feature. Caching interception, that's also optional. We have a capabilities API, so you can consume what options are provided by the provider. Okay, so we have these two classes give you helper methods, and you can say whether or not the feature is supported in the provider. Okay, standalone versus distributed. If you're a standalone in a single VM, we can give you store by reference, the store by reference option, which gives you speeds similar to concurrent hash map. Cache event listeners are very useful for triggering events in a standalone environment. If you're in a distributed environment, we're going to give you store by value, because a reference in a distributed, in a distributed setting, a reference loses its meaning really. We short circuit some things that you would expect to see in a map API, like there's no values method, and the remove method doesn't return the object; it just returns a boolean. So things like that. There's no need to have much detail. So we short circuit some of the things you expect to see in a map. JSR 107 is not a grid specification. JBoss's InfiniSpan, Oracle Coherence, and IBM's ExtremeScale, those are all data grids. EH-cache and Memcache are distributed client-server caches. Monique Sertani, who heads the JSR 347 specification, he's also a very strong contributor to JSR 107. The difference between 347 and 107 is that we don't mandate a topology. There's no in-place specification for the topology of your solution. JSR 347 does specify that. Class loading. Class loading is very tricky when you get with caching solutions. If I have a JBoss application server and I have A.war and B.war, and each of those wars contain an employee.class, and the employee.class is bytecode for bytecode identical. If A.war, if its class loader loads employee.class into the cache, okay, and then mutates it, and then B.war, its class loader loads employee.class for the purposes of reading from the class, does anybody know what will happen? Yeah, class cast exception, exactly. This means that, and it's because even though employee.class and employee.class are bytecode equivalent, they're not the same, because A.war has a class loader and B.war has a class loader. So we solve that problem by specifying, when you create a cache manager, okay, you have to specify a cache manager's class loader, okay? That prevents that problem of employee cannot cast to employee, which drives people bonkers. What else? Okay, we support 2 ways of creating a cache manager. We have the service loader creation, which is part of Java 6, and we also have, you know, the new constructor, which you know, is familiar with everyone. One of the important things to note is that when you're loading a cache manager, you want to include the notion of the cache manager's class loader. Okay, that's important. Okay, how do you create a cache? Well, you'd have to really go to the API to see this fluently, but we use what's called the fluent builder pattern. So as you do set certain parts of the cache, we return a reference to that cache manager. So you can just everyone knows the fluent builder pattern from Joshua Bloch's book. It's very powerful way. We adopt that for building cache managers and for specifying what features are set in your cache manager. Yeah, yeah. Okay, just a couple more. We have a method called unwrap. This is a way to get to the underlying provider's proprietary API. We were going to call this method lock yourself back into proprietary caching code, but we decided we'll just call it unwrap. Okay. Annotations. I guess we could just skip the annotations part. Just know this: we have a rich way of specifying annotations. It allows you to give cache consequences to code that already exists without having to write caching code, if that makes sense. You know what I mean? Okay. More information on this. Everything is available on GitHub. Everything's completely open. If you want to pull down our API artifacts into your build environment, we have an artifact registered in Maven Central. We're on the 0.6 version. Okay. Let's see. That's the end of it basically. I want to acknowledge Greg Luck and Cameron Purdy. Much of this PowerPoint was taken from their Java 1 2011 presentation. I want to give them credit for that. Okay, so that's it. Yep.
Thanks, Ben. That was great.